Sounds good. I have the pleasure of working for Lithium Americas Corporation full-time. I'm based in New York City, where I am currently. And what I'm going to present today is basically on the origin of the Thacker Pass lithium deposit, which is the largest known lithium resource in the United States. And before I get in, this work is only part mine that I've worked on. There's been several other people at Lithium Americas, at UNR, especially Mike Gressel, James Ingraffia, who did a master's on this project, Michael Rapetta, who's doing a master's based out of Canada, Rachel Hampton, conversations with Steve Castor, Chris Henry, Lisa Stillings, and Jim Rytuba, all have really helped. We all work together to sort of bring this to where it is today. And it's by no means a perfect Genesis model on the origin, but I think pieces of everyone's sort of perspective have come together to really paint the most comprehensive. Most comprehensive picture yet of how this massive lithium deposit formed. And the reason why we're doing this is because most of us are watching on our computers right now, but in our pockets, or maybe your smartphone, it has a battery in it, which has lithium in it. And famously, these are some headlines for the past month alone. Tesla is the biggest proponent of electric cars, and electric cars is really what's driving the newfound demand for lithium. We also have other electric vehicles like the Leaf. GM just announced that they're making an all-electric Hummer, which is the antithesis, you would think, of an electric vehicle, but that's happening within a few years. And now they're even getting to manufacture. In Europe, they're really leading the charge there, where 60% of the cars sold in Norway last month were electric. And even on the political spectrum, both Republicans and Democrats in the United States are showing their support for the electrification of the automobile industry as a realization of what's to come. And an article out last week even showed that the leading Democrat, or the Democratic candidate for president, even supports domestic mining of EV minerals. And that's a friendly reminder to make sure you vote next week. So the reason for this demand is, like we just saw, electric vehicles. And this is on the left is a plot of the tons of LCE, and you'll see LCE a lot in this talk, and that stands for lithium carbonate equivalent, which is basically lithium carbonate, a multiplication of about 5.3 from pure lithium metal. And it's what people in the lithium industry use to kind of. And so we can see that several studies have shown, and it's hotly debated between different people, but it's about a 20% increase per year projected of demand for lithium. And as you can see right now in the upper right-hand corner, most of the production, this is data from the USGS in 2017, is concentrated in a few small countries, specifically Australia, Chile, and Argentina. The United States has only one actively producing lithium operation in the Silver Peak mine in southern Nevada, and that's only a very small percent of global production. So most of the demand will need to be sourced from the US. If the US wants to consider this as a critical mineral, we need to really focus on domestic production of lithium resources. And so the objective of this talk is to review how lithium deposits of lithium form, and we'll have a specific focus on how the Thacker Pass project in northern Nevada forms, as it is the largest known resource in the United States. And a brief outline of what we'll go through. We'll go through the different types of deposits. We'll go through the general geology of the Thacker Pass deposit and its host, the McDermitt Caldera. We'll discuss the three components that we're proposing as the origin of the sedimentary lithium deposit at Thacker Pass. And then we'll end with some concluding thoughts. So first, how do lithium deposits form? Lithium's the 25th most abundant element on Earth. But despite this, it's only really economically viable to mine in three types of deposits. The first being pegmatite or hard rock deposits, such as the green bushes in Australia. We have brine deposits like the Calchari, Olaroz, project by Lithium Americas in Argentina, as well as the neighboring in Chile. And finally, we have the third and newest, so to speak, type of lithium deposit, not geologically newest, but new in the minds of the mining world, sedimentary or clay-hosted deposits. I prefer the term sedimentary over clay because there are many different types of resources out there, and they're not, that form in a sedimentary environment, and they're not all clays. So it's traditionally been called clay, but I prefer a transition to calling them sedimentary deposits. But I'll use them interchangeably in this talk. There are several geological and environmental processes that lead to the enrichment of lithium in all three types of deposits. However, they all have one component in common, which is that lithium prefers to be in the state of highest entropy. What does that mean? In simple terms, it means if you have a solid, a liquid, and a gas, the lithium will prefer the gas over the liquid and the liquid over a solid. And that one principle will help us understand how all types of lithium deposits form. So if we start way back in time, the formation of the Earth, we had a bunch of planetesimals colliding to form basically the composition of a meteorite, which was the Earth. So that's step one. Step two, and this is happening over billions of years, you have what's called Earth differentiation, where the heavier metals like iron and nickel sunk to the middle of the Earth, forming the core, and the lighter elements like lithium, lithium is number 3 on the periodic table, it's the lightest metal, floated, so to speak, to the surface of the Earth, forming the lithosphere or the crust. So that's step 2. And if we zoom in on the tippy top portion of the crust, we'll see step 3. And this is what we call enrichment in the crustal in the magma chamber. And this was a focus of a chapter of my PhD with Gail Meho at Stanford. And the main principle that we talked about earlier, where lithium wants to be in the liquid over a solid, really holds here. Because when you introduce a magma to the crust, or the crust starts to melt due to enhanced thermal gradient or one reason or another, the melt that forms in the crust, lithium will want to partition preferentially into that melt. And that's called being an incompatible element, but you don't need to remember that. There will be a quiz at the end, but you don't need to remember that one. So now we're on to step 4, and this is where the different types of deposits start to diverge. And first, I'll start with brine deposits, which, like they said, mostly occur in South America, as well as at Silver Peak in Nevada, the one producing a lithium mine in the United States. So you have your magma chamber that has some lithium in it for one reason or another. And then you have some eruptions that come from that magma or maybe a different magma source. And during that eruption, about 45% of the lithium is lost to the atmosphere during gassing, because as the lithium escapes, it's a very gaseous eruption usually. And because the lithium prefers the gas over the solid state, liquid state, it will mostly escape. And those numbers have been really studied well by Al Hofstra and others at the USGS based out of Denver. And so now you have your lithium, whatever is left of the lithium is sitting in rocks, typically volcanic rocks like lavas, tuffs, and ignimbrites. In this talk, we use tuff and ignimbrite interchangeably, but they both mean any sort of volcanic rock that is extrusive that erupted explosively rather than effusively. So you have effusive rocks like lavas, you have explosive rocks like tuffs and tephra, and predominantly composed right after eruption of volcanic glass. And when you introduce meteoric water, such as rainwater, groundwater, maybe a minor hydrothermal system, you introduce water into contact with the glass in that rock, which pairs lithium. And once again, lithium doesn't want to be in the solid. It'll want to jump into the liquid and complex with ligands like chlorine, and that will then accumulate in the nearby basin of the watershed. So what happens preferentially over about 1 million or a couple million years is you have the lithium being leached from the volcanic rocks and accumulating in the nearby basin. In the case of the Salar de Atacama and Salar de Cachorro in South America, you have high rates of evaporation because you're very high at elevation. You're at 4,000 to 5,000 meters.
Invest in Primark.
You have 4,000 to 5,000 meters of elevation, so you have high rates of evaporation, and that when the water leaves, it leaves behind the lithium-enriched brine, which then companies can come in and extract that brine from the subsurface. And if you look at a map of global lithium resources, brine deposits are the blue squares here. And if we zoom into South America, you can see this place called the Lithium Triangle. It sort of looks like a triangle, but if we want to know why it's called the Lithium Triangle and we zoom in even further, we can see this topographic map. You can see 100-kilometer scale at the bottom, and in blue are salt flats or salars. You can see all the companies that are either under exploration, development, or actually production in this region. So it's a very concentrated region of lithium extraction, accounting for about half of the world production of lithium at the moment. The Calchari-Olaroz project in South America, this is what it looks like on the surface of the earth. You have some mud cracks. We do exploration drilling to access that brine at depth. And once you access the brine, how you process it is that you pump it deep out of the earth and you pump it into giant evaporation ponds. These are pretty shallow ponds, and in the case of the Lithium Americas and Minera XR property down there, the ponds are about 1 kilometer wide and several kilometers long. So you can see these features from outer space. They're actually quite beautiful. And so how you develop a project here is you develop a hydrogeologic model where you look at the different depths through the exploration drilling. You characterize the stratigraphy, like the different colors you see on the left-hand side. And you can see on the right-hand side is in blue is the Lithium Americas or Minera XR resource. And all the dots are the different places where we have drilled to understand the geology of the resource, as well as the subsurface brine chemistry. So you create a geological model, and then you can measure the lithium concentrations. You can see these are cross sections of the salar at depth, going down to, what is that, like 600 meters or so of depth. You can see the range in brine concentrations from anywhere below 100 milligrams per liter, which is approximately equivalent to ppm, up to 700 ppm lithium. And then you access that brine, you pump it in, evaporate it to higher concentrations, and then you can process and make your lithium chemicals for batteries. So that's the first and most easily accessed and cheapest currently type of lithium deposit. The second one are hard rock or pegmatite deposits. And similarly to the other ones, you have the formation of a magma chamber where the lithium is jumping into the magma because it doesn't want to be in the crust. And then you have cooling of the magma chamber. And I like to think of this as most of us have used ice cube trays before, where you fill up an ice cube tray with water, and you put it in the freezer, and you start to cool it. The same thing is happening here with our magma chamber. You're taking your water, in this case magma, and putting it in a cooler, in this case the crust, which is much colder. And this is a very simplified general model. This is by no means what happens. It's just to illustrate this point. So what happens preferentially, because lithium doesn't want to be in the solid, as you start to crystallize the magma chamber, it'll preferentially want to stay in the melt because it is incompatible. And so as you keep crystallizing, or in the case of our ice in the freezer, you keep crystallizing the edge of that ice until the middle of that ice cube is just about a little bit of liquid left right before it completely freezes. At the moment where this is almost done, there's little bleb of magma left in the chamber. This magma is very volatile rich. It has a lot of lithium. It has a lot of other sexy ore minerals we like to think about, a lot of fluorine, chlorine, and then you cut off the heat source and you completely crystallize, and you put your ice cube in your drink, preferentially a vodka soda, I would say. But after millions of years, hundreds of millions of years of uplift and erosion, you can then have this pegmatite be exposed at the surface of the earth, and then you can come mine it out like they do in the green bushes, as well as a project that's under exploration stage in Ireland, diagenetic lithium. This is you can see the stippled pattern on the left side of the map is Leinster granite. It's several 100 million years old, and then there's Ordovician metasediments is the white pattern. And there are a bunch of pegmatites that have been mapped along this continent. People believe that the presence of pegmatites and lithium there has to do with this interaction. And I had the chance to go there to do some work. And this is just a side note. It's a really interesting place to do geology because the geology of Ireland was mapped not using bedrock because there's a lot of soil covered there, but because of the boulder fences between properties. Hundreds to thousands of years ago, when people were trying to cultivate their property, they would take rocks and put it on their property boundary to mark where they would farm and whatnot. And nowadays, you're not going to take they weren't going to take a rock from Northern Ireland and bring it down to their wall in Southern Ireland. So the whole geology of Ireland was pretty much mapped through these walls, which is a fascinating historical geology note. But it ties into lithium because the way these pegmatites were found was because in these rock walls, people were finding the lithium pegmatite mineral called spodumene, which you can see on the right-hand side of the screen. There's a pen per scale. And these are giant crystals of lithium-bearing mineral, which are mined in these hard rock deposits. Now, a lot of exploration holes have been drilled. You can see these laths of spodumene as well in the drill core. Some academic studies have been done to analyze these as well as others around the world. But you can see that in this case, this project is not under production or even development. It's still under the exploration stage. So there's a lot of different types of lithium out there, projects out there at different stages. An interesting point up here is just south of Dublin. If you go up, you can actually see these intrusions, the granite intruding the Ordovician metasediment very beautifully, and beautiful aluminous minerals. It's a metamorphic petrologist's dream. If we look at another one that's actually under production, is the Pilgangoora area in northwestern Australia. You can see on the right-hand side of the screen, Altura and Pilbara's properties, and their different drill holes are blue and orange, and their proposed pits. Some of this is active as well. And you see the red lines, if you can see them well, are the pegmatite veins. And there's been a lot of work done in this region. Pilbara has some 3D modeling. If you go to their website, you can see where their pits and their future pits are proposed. You can toggle on and off some things. So I would recommend going there if you're interested to learn about pegmatite deposits. So finally, the third type of lithium deposit are sedimentary lithium deposits. And this forms in a very similar way to brine deposits at first. You have lithium-rich magma or two that for some reason or another decides to erupt. In the pegmatite model that we just went through, the magma doesn't erupt, but in the brine and the sedimentary deposits, the eruption occurs. Once again, a lot of the lithium is lost to the atmosphere during the eruption. However, you are left behind with some relatively lithium-enriched glass within lavas and tuffs on the surface of the earth. Now, after thousands to millions of years of erosion and weathering, the lithium will preferentially be leached from those rocks again and accumulate in a nearby basin. And what you have, if it is a closed basin, you have closed hydraulic system diagenesis. And we'll get into this in a little bit. The diagenesis essentially means that the tophaceous material that's in the sediments in that lake, under its own thermal profile, will alter from glass into clay. And so this is how the sedimentary lithium deposit is formed. And after the lake is done, it drains for faulting or whatever reason. You can then come in and scoop the lithium off the surface of the earth. And an example of this deposit is in Clayton Valley, Nevada. This is the Cypress Developments Project, just adjacent to the only active lithium mine in the United States, the Silver Peak mine. You can, and on the map on the right-hand side, you can start to see the Silver Peak property in the upper left-hand corner. This project, they've drilled about 28 drill holes, and they just came out with a mineral resource assessment in August, saying that they have 5.2 million tons of lithium carbonate equivalent M&I measured and indicated using a cutoff of 900 ppm. That means anything below 900 ppm in their rock, they ignore. Everything above it, that's what they use to count. And the average in their ore, in their resource, is about 1,000 ppm. And so this is a map of their claystone zone 1. And you can see it's roughly, I'll go back to this guy, you can see it's roughly at the same location. you can see the bar on the right-hand side showing the range in concentrations of their deposit, and it ranges from about 900 to 1400 ppm, were in their clay, in their zone 1. And on the left-hand side, you can see their genetic model is similar to what I just presented, where you have an input of tuffaceous material into the basin that then undergoes diagenesis from the lithium. Now that brings us to Thacker Pass. Thacker Pass is a sedimentary lithium deposit, but my role tonight is to try to demonstrate to you that it's a different type of sedimentary lithium deposit. And why do I say this? One, it's because it's been known for a very long time that this deposit exists. It was first drilled out in the 70s by Chevron, actually. We're looking for uranium and came across lithium. And so since that time, there's been over 400 drill holes that have been drilled in this region, all over the caldera, but principally in the southern part of the caldera where the Thacker Pass project is. On the right, you can see this animation, hopefully, that I made in MATLAB, which shows the location of the drill holes and the concentration of lithium. And the concentration of lithium from cold to hot colors is here from about 1,000 to up to 9,000 ppm lithium. Compare that to the max that we saw at the Clayton Valley project, which is about 1,400 ppm lithium. And so the average resource in the Thacker Pass, the average concentration of the resource at Thacker Pass is about 3,000 ppm lithium, and that comes to a 6 million ton LCE resource using a 2,000 ppm cutoff. So we're, in this case, ignoring everything below 2,000 ppm lithium. So we're only counting things above that. So if we were to use the same cutoff at Clayton Valley, our resource estimate would be significantly higher. We've done some simple calculations to show that it would be at least 3 times higher than 6 million tons. And so as it currently stands, we would not even process any of the material that's in the Clayton Valley project. And I say this in no way to disparage that project or any other project, just to point out there is an order of magnitude difference in the volume and the mass of lithium at the Thacker Pass project compared to any other sedimentary resource. And so the purpose of this talk is to answer the question, why is Thacker Pass such a large and high-grade resource? And people have attempted to do this and have done an amazing job understanding the geology, the mineralogy, the petrology, the volcanology, all the aspects you need. And all of that information came together so far in Castor and Henry's 2020 paper that came out a few months ago. They did a very rough back-of-the-envelope calculation showing that the whole Caldera Lake sediments at McDermitt Caldera contain 640 million tons of lithium carbonate equivalent. And in the Thacker Pass, component of this is only 6 million tons or 8.3 million tons. So clearly there's a lot more lithium in the caldera, and we want to understand why is it there. So I'll give you the punchline of the talk right now, and it'll be my last slide as well, so hopefully I do my job. The punchline here is that Thacker Pass is of exceptionally high grade in size relative to the other sedimentary lithium deposit, and that is because it formed within a caldera atop a thick degassing intracalderic membrane. And this is a unique feature that's not observed in any other sedimentary lithium deposit. So that brings us to, that was a very long intro to the geology of Thacker Pass in general. And before I get into that, I want to reemphasize the point that this work is only very small percentage of my own and my collaborators. There's been a long history of detailed geological and resource-related research at McDermitt. In the 80s, the USGS led seminal work on the geology of the whole McDermitt caldera, volcanic field. And that was followed by work by Steve Castor and Chris Henry and others in Nevada to understand the geology more as well. Will Starkle at Washington State with his advisor John Wolfe and others really redefined what the caldera at McDermitt was, as well as work in part during my PhD at Stanford doing the physical volcanology in geochronology of the McDermitt Caldera and calderas to the north. The McDermitt Caldera is also really spectacular and I would say weird almost in how many different types of ore resources there are. There's mercury. At one point, it was the world's largest producing mercury location. There's uranium mineralization. There's gold. There's obviously one of the largest, if not the largest, lithium deposit in the world. Work by Jim Rytuba and others, and Dave John showed that there is gallium enrichment and rare earth enrichment. So there's a lot going on, and the USGS led this work in the 70s and 80s, and Steve Castor and Chris Henry continued that, Jim Rytuba, and then bring forward to this century where Cloud Morissette with the advisors Lisa Stillings at UNR did this incredible thesis on understanding the mineralogy of the clays at Thacker Pass. And so they did a lot of work comparing it to hectorite and other locations to understand was it dioctahedral, trioctahedral, and a bunch of very complicated XRD work that's beyond the scope of what we're going to talk about today, but it was very important for understanding the genesis of this deposit. Then part of my PhD work on why the McDermitt Caldera is enriched in lithium. And finally, this year, 2 papers, the one that I mentioned already by Castor and Henry, that talked about the genesis of the lithium-enriched rock at McDermitt, as well as James Ingraffia, who I assisted with Mike, where we presented a bunch of the information that I will be presenting now. And that is in this volume of the GSN Symposium. And so I encourage you to read it when you get the chance. It's a really good paper. So if we step back in time, how did McDermitt Caldera form? McDermitt Caldera, you can see in the maps on the left-hand side, is straddles the Oregon-Nevada border, and it's a caldera-forming eruption similar to Yellowstone, where you spread ash across the continent, that occurred at about 16.3 or 16.4 million years ago, depending on idiosyncrasies of argon dating. You can see this trend, weird trend of volcanic centers on the map on the right-hand side of the screen, and those numbers correspond to millions of years ago in terms of when the major caldera forming eruptions happened. And it forms this very peculiar trend, similar to like a trend you see in Hawaii. If you've been to the Big Island of Hawaii, there's a big island, and then there's this trail of volcanic islands that go down to seamounts as you go north towards Russia. And I like to think of this forming as if you held a piece of paper out, and then you lit a match under it, and you start to burn that piece of paper. That match is a hot spot, which is what you can see on the bottom left corner is a hot spot in the mantle underneath Yellowstone, and it's where it currently is, or underneath the Big Island of Hawaii. And now, if you step back in time, that hot spot was once under the McDermitt Caldera. And if you have your piece of paper, it's still burning where the active volcano is, then you start dragging your piece of paper over that stationary hotspot. And the paper in this case is the continental crust. You leave behind this trail of burn marks and then an active burn on this end. And what that is recording is this basically a tear of this hotspot or a burn line in your paper, assuming the whole paper doesn't catch on fire. But basically it illustrates that McDermitt is Yellowstone day one. What was happening at Yellowstone, now happened at McDermitt 16 million years ago. And so now we'll go back to our not to scale models to understand lithium deposits. So similar to brine deposits, you have this lithium enriched magma that forms in the upper crust. And then instead of some small eruptions, you have catastrophic eruption of the magma chamber due to a variety of reasons. And a lot of people debate this. Is it vapor saturation? Is it faulting? But there's, for one reason or other, this magma says, I want to get out. And what happens is that volume of tuff, in the case of the McDermitt tuff or the long-ridge tuff that formed the McDermitt Caldera, has about 1,000 cubic kilometers of material. And that material erupted as Plinian eruptions, pyroclastic flows. If you ever seen the video of or the picture of a volcanologist in a truck trying to outrun the pyroclastic flow that's about to consume them, that's sort of what's happening here. And this ignimbrite or tuff spreads for about 100 kilometers away from the vent in some cases. And what happens? All that 1,000 cubic kilometers of material that was underneath the surface of the earth, you're not going to have a giant cave. So what happens, that roof of the magma chamber, you can see by those squiggly lines, it collapses and forms caldera or a cauldron. You can think of a place like Crater Lake in Oregon as a small analog of this. And so all of that tuff that erupted in that chaotic way, it's a glassy mix of pumice, ash, crystals, pieces of the wall rock that were ripped off as it escaped, then settles out and forms what's called a tuff or an ignimbrite in two locations. One is the intra-caldera tuff, or the tuff that's inside of the cauldron, typically up to a kilometer thick. Then it also forms the outflow sheet, which extends to 100 kilometers away from the vent, and that's what I'll refer to as the outflow sheet of the ignimbrite. And so that's sitting on the surface of the earth, and what happens? Similar to the brine deposits, you have leaching of the lithium from these volcanic rocks on the surface of the earth due to meteoric and maybe some hydrothermal fluids. So that lithium will jump into the water, complex to chlorine or other ligands, and accumulate in the caldera lake, providing mass to the system. You can then also have diagenetic sediments that accumulate in the lake, and those can undergo mineral diagenesis to also provide a mass of lithium to the system. And this is what the McDermitt Caldera looks like from outer space. If you go to Google Maps or Google Earth, it's a beautiful caldera. You can see the nice keyhole shape in the town of McDermitt on the upper right. And the recent work by Chris Henry, Will Starkle, Steve Castor, and others have really done a great job documenting the different stages of collapse of this caldera, following on the work of Jim Rytuba and others at the U.S. Geological Survey. Recent work that we've done at Lithium Americas has done some geological mapping of the southern portion of this area. You can see the hatched area in the middle shows the location of the lithium resource that's measured at about 6 million tons lithium carbonate equivalent. And as cartoon cross-section of this shows what this looks like. You can see the cross-section line southwest to northeast on the map on the bottom. You can see that you have this basically bowl of ignimbrite over which the Caldera Lake sediments, which host the resource at Thacker Pass, occurs. And so what has Lithium Americas done to get to this resource assessment to be the largest known lithium resource in the US? As we talked about before, there's been an extensive drilling campaign with over 400 holes and counting of understanding where the lithium resource is, and it's remarkably consistent. We've looked at a bunch of different elements, including fluorine, lithium, rubidium, magnesium, calcium, and really trying to understand the distribution of the lithium and other potential problems from a processing standpoint to really understand where the best place to mine this sediment would be, because we can have our pick. We can mine anywhere within this caldera and find high-grade lithium, as you can see with the animation. We've also done a bunch of geophysical surveys. On the bottom right is the result of a seismic survey we've done. The yellow line indicates the top of that intra-caldera tuff, and overlying that are the caldera lake sediments where the resource is. And you can overlay some drill hole data to see that throughout basically the whole thickness of the caldera lake, we have grade greater than 2,000 ppm. So this is a very consistent, large resource. And as you can see from the cartoon map on the left, the Thacker Pass project is that little bleb in the whole giant caldera. None of the other part is included in that. And this 6 million ton LCE M&I resource is, like I said earlier, significantly less, 2 orders of magnitude less than the 640 million tons of lithium carbonate that's approximated by Castor and Henry. So we need to figure out, where does the lithium come from? And that's this section of the talk. So there are what we'll propose is that there are 3 main sources and components of this lithium deposit. One is you have the leaching of lithium in brine deposits. We have the diagenesis that happens of the basal tufaceous sediments to form these lithium-enriched clays like smectite and illite within the caldera lake. However, what differentiates this from everything else is the widespread and prolonged degassing of the underlying intracaldera tuff that adds especially large masses of lithium to the system. And so to get at component one, we're going to jump back to South America and look at brine deposits again, because this is the main factor in driving brine deposits. Now, a lot of work has been done by researchers at the University of Alaska Fairbanks, UMass Amherst, and Rutgers to really understand the genesis of lithium brines in the Atacama, especially in Salar de Hombre Muerto. So this is just the first part of that equation, which is where does the lithium actually come from, not how does the brine form itself. And so what I did with co-workers, Ariel Bregman and Marcella Cassini at Lithium Americas, you can see them on the left, in an outflow sheet of the Cerro Galán ignimbrite at the Salar de Hombre Muerto. What we did is we went around the three major producing salars in South America, Hombre Muerto, Cauchari-Olaroz, and Atacama, and we collected tuffs from the watersheds of those three salars to try to get a mass of lithium possible input to this brine deposits. And as a refresher on the upper right, you can see what, if you grab a piece of tuff, you'll get an ashy matrix, which is the bulk of it. In many cases, you'll have pieces of pumice, you'll have little crystals like quartz and feldspar, as well as pieces of extraneous pieces. But what we're after is where the lithium resides, which is in the ashy matrix. So what we did, as you can see in the middle, these are shrimp mounts, which aren't the creature you like to eat. It's the ion microprobe based at Stanford University. And each one of those mounts is about an inch wide. And they're little pieces of glass and some other phases on there that we mounted to do 10 micron analyses to see how much lithium was in the ash. And the results are pretty interesting. They're color coded based on the different pipes. You don't need to worry about the details, but look at the left axis or the y-axis, in which you can see that the lithium concentrations in the ash itself are going up to 200 ppm. There's one case where it's over 1,000 ppm. I didn't include that because I wanted you to be able to see all the beautiful fractionation trends you can see with these two incompatible elements. So the highest one, for example, is the Corinzuli tuff, which is in the northern part of the Cauchari-Olaroz salar. And the theory here is that the lithium in these tuffs are providing the lithium mass for the brine deposits in the salars. And this is another place I'm going to quiz you later. You're going to have to memorize these equations. But that's a joke. The lithium mass can be calculated due to a variety of ways. This is just a simple mass calculation, assuming that 45% of the lithium during the eruption is lost. So if we zoom in to the Cauchari-Olaroz salar, and we do this mass calculation using the concentration we measure in the tuff, the volume of the tuff, the percent of that tuff that's within the watershed, because that's what's important. If it's outside the watershed, it's not going to contribute to the brine within the watershed. And we use some other things like the percent of ash in the tuff as well. We can come up with simple masses of lithium that's within the tuffs within the watershed. And in the case of Cauchari-Olaroz, if you look, the total lithium available for leaching is almost 45 million tons, 45 million tons of lithium carbonate equivalent. Compare that to what the known resource in all three projects in the salar is about 30 million tons. So clearly, there's several orders of magnitude greater lithium available than what is actually measured in the brine. And even if you only take 1%, if you leach only 1% of the rock, and you do this exercise for all three, you can see that there's clearly more than enough lithium to provide the mass for the fluids that are ending up in the brines itself. So if we jump back up to North America and the Thacker Pass project, this is much older than those ignimbrites were erupting a couple million years ago. This was tens of millions of years ago. There's been significant basin and ridge expansion you can palimpsestically restore the northern Nevada, southern Oregon to understand it, but you won't have very pretty maps. It'll be more disjointed. But here on the left is a map from one of my papers from my PhD, where we looked at different outflow sheets to try to estimate the total volume of tuff. And if we do a similar calculation for assuming that only 20% of the outflow is within the watershed of the McDermitt Caldera for the Long Ridge tuff, which is the tuff that formed the McDermitt Caldera. Some people use McDermitt tuff. I prefer Long Ridge tuff for a variety of reasons, but we don't have to get into that. If you assume that only 20% of the outflow is within the watershed, and you do the same calculation, this supplies approximately 90 million tons of lithium carbonate to the Caldera Basin. But that is only, if you say all of that happens, and that only accounts for a very small percentage of the total that's estimated by Castor and Henry to be in the Caldera. So clearly we need an additional source. And that's where, so that was our first source. That's where the diagenesis of tufaceous sediments to form lithium-rich clays comes in. Diagenesis is a pretty well understood phenomenon, but before we jump into that, I want to quickly go over, this talk is not going to go into different types of clays and structures of clays and spacing of different clays, but I will want to differentiate between three types of clays. One is detrital clays, which means that you erode a rock somewhere and that little clay particle ends up in your basin. The second is neoform clays, which means in your water column, you create the chemical conditions under which a clay can precipitate directly from solution, which is called neoformed. And the third is a transformed, which is diagenesis, in which you have secondary alteration of existing material, in this case, volcanic glass, and this happens during deposition, burial, and diagenesis. And so that's the main type of clay that we're focusing on in this scenario. And so it's very well understood. It's been studied in places throughout the Western US for several decades by the USGS and others. And basically what happens during diagenesis is glass, like what we have right here. I don't know if you can see this. This is a piece of glass from the McDermitt Caldera. It's a beautiful green banded obsidian. And so you might recognize this as obsidian, but when it erupts basically effusively, like as lava, it can form this. But if it erupts explosively, it can form what's called tephra, or a little ashfall, which in Mount St. Helens, people in eastern part of the state were wiping tephra or ash off their cars. And that's sort of what we're talking about. So this glassy material that accumulates in the lake basin, it's very unstable. Glass does not have a chemical or bonding structure. The lithium in here is not bonded to anything, so it's free forming. And so it's very unstable, so it wants to be stable. And so you can see images on the right of glass shards under microscope. There's a 50 micron on the upper left bar for scale. And what happens is during diagenesis of these tufaceous sediments, you have basically, if it is in a closed basin where you have high rates of evaporation, you increase the alkalinity, the salinity of that pore water. You also have, the glass itself that's contributing to the alkalinity because it has lithium, it has potassium and sodium and other things in it. And so what happens is all of a sudden you start to stabilize the formation of diagenetic minerals. So on the cartoon on the bottom, you can see this section of tufaceous sediment. You can see what the temperature is like. It goes up to about 70 degrees C in McDermitt. And what the typical profile, you start with a smectite, you have a mixed layer in the middle, and then it goes down to an illite with depth. And this transition from smectite to illite is seen throughout marine and terrestrial basins throughout the world. And so if we zoom to McDermitt, a lot of work done by Claude Morissette and Lisa Stillings, as well as recently by Castor and Henry, have really demonstrated the smectite to illite transition to be present at McDermitt. If you look in the middle, you can see a fence diagram and a rough outline of the pit shown when you can see in each location, in each drill hole where they've done an analysis, XRD analysis of the clay, you can see the smectite to illite transition. So we're pretty confident that diagenesis is occurring. We know the sequence of sediments was up to 200 meters thick. In some places, maybe even up to 500 or even a kilometer. There's some evidence for that. And what happens here is at McDermott, we know the lithium is enriched because of the work we did at Stanford to understand that there's a lot of lithium in the tuff and glass to begin with. And as that undergoes burial diagenesis in a closed basin, which is really important because if it wasn't closed, the lithium would escape. You have to have a closed basin. You eventually form these lithium smectites or hectorite, although there's some debate, as Castor and Henry point out, whether it's actually hectorite or not, as well as lithium illites, which some believe could be the mineral taniolite. So basically, most basins across the world with, most sedimentary deposits have diagenesis, and that's it. And that can explain their enrichments up to 2,000 ppm. However, this is not a sufficient model, a genetic model for Thacker Pass. Ooh, and I don't know what's going on there, those blue lines. Basically, Castor and Henry calculated that the diagenesis of tufaceous sediments at McDermitt Caldera led to approximately 120 million tons of lithium carbonate. Can you guys see those blue lines? I don't know if you can.
Yeah, we can.
Maybe my computer's biting the dust. Anyway, so if we add that 120 million tons of LCE from the diagenesis to the 90 million tons that we saw before, we can see that that comes to 210 million tons of lithium carbonate, which is nowhere near the 640 million tons Castor and Henry estimate. So an additional lithium source is needed. And we think, this is work done by Mike Ressel, James Ingraffia, that this can easily be accounted for by the introduction of higher temperature lithium-rich fluids to the system. And this isn't a new idea. This is actually has been observed in a marine sequence in the Sea of Japan, where if you look at lithium on the x-axis and with depth, it's a much deeper profile, but the point is the same. They have minerals that are consistent with relatively low lithium. With depth, they're consistent with diagenesis. However, at the base, right over a hydrothermal system, they see anomalous lithium enrichment and also a weird hydrothermal lithium mineral called lithium tacitite. And this is from a paper in 1996. And this is pretty interesting because look at what we have here. If you look at the right-hand side, where you have the lithium profile from roughly 2 to 4,000 straight down, but then towards the base, right above the intracaldera tuff, we have a significant lithium enrichment. And we also have what's known to be a weird lithium illite, as shown by Castor and Henry and Morissette as well. And so what this says is that this is supportive of the idea that the degassing intracaldera tuff in the sedimentary section is adding additional mass of lithium to the system. And this is what differentiates it from other deposits that just undergo burial diagenesis. So let me see if I can just quickly escape. And then, oh no, I think it's my, I think we're gonna have to learn to live with blue lines. All right, so what we see at other sedimentary lithium deposits are the first two steps. And the third step is unique to Thacker Pass deposit, which is the widespread and prolonged degassing of underlying intracaldera tuff that's adding additional mass to the system. Castor and Henry advocated in part for a hydrothermal component in their paper recently, citing relatively high concentrations of ore metals like sulfur, molybdenum, and arsenic, things we like to see in porphyry or epithermal systems with depth. You can look at their profile and see the different concentrations. Lithium is in red, potassium in green, arsenic in amber, molybdenum in blue, rubidium in purple. You can see all towards the base of the section, they all show this weird spike increase. And so this is consistent with some sort of higher temperature fluid. They also note that the authogenic formation of albite replacing null seams and zeolites is additional evidence for alteration temperatures that are above the boiling point. Because they say that the diagenesis must have happened probably below 70 degrees C. So we know that there's some high temperature fluid coming in. However, we think that it's not a classical hydrothermal system. When you think of a porphyry or epithermal system, you have these really localized systems. And this, I don't think, is the case that's happening at McDermitt for a variety of reasons. One is that the lithium enrichment that we see is widespread throughout the whole caldera. And it's not just confined to ring fractures or above fractures that could have acted as conduit for a classical hydrothermal system, like we see in the northern part of the caldera associated with the mercury mineralization. In addition, the hydrothermal metal concentrations that we see up to 300 ppm molybdenum are much higher than typical diagenetic systems, which is at least an order of magnitude lower, but not as high as we see in epithermal systems like copper molybdenum porphyry systems get up to 3000 ppm molybdenum. So clearly there's some sort of middle ground here between diagenesis and these epithermal systems that we can see based on the concentration of these metals. The third point I'll make to why this doesn't fit a classic hydrothermal system is because lithium and other trace metal concentrations are consistently high grade throughout the basal section, and there's no high grade vertical component. So there's no like vertical rise of a hydrothermal fluid that's bringing the lithium with it. So that's further evidence that we likely don't have a classic hydrothermal system here. Finally, there's a silicious hot pond zone, we call it, right above the intracaldera tuff, ubiquitously throughout the deposit, with these high temperature silica, amorphous silica features that indicate that there was high temperature input to the system right above the intracaldera tuff. And so we proposed in James's master's work that these observations, as well as the additional mass supplied to the system, can be explained by degassing and devitrification of a very hot, thick, and vitric intracaldera tuff underneath the sediments. And I emphasize hot here because I think that's a really important metric. But before we go into heat, I just want to show you a figure from James's paper, which shows the lithology on the left column. But the two columns I wanted you to look at are, you might not be able to see it too well, but it's the blue and gold column, which is lithium concentration. That's blue is lithium between 2000 and 4000, and gold is lithium between 4000 and 8000 ppm. You can see it is enriched with depth. Now, if you look a couple columns over at sulfur and arsenic, which are hydrothermal indicators, you can see that those hydrothermal indicators are high only in the basal part of the sequence associated with the especially high lithium concentration. So now back to our hot. There's a reason why I made it all caps. The emplacement of the McDermitt tuff was at very hot temperatures. They believe by work done by Hargrove and Sheridan in 1984 at about 800 degrees Celsius. And this is because it's called a peralkaline magma. It's sourced from a peralkaline magma. My PhD advisor, Gail Mahood, Wes Hildreth, and others have done a lot of work to understand the reasons why peralkaline magmas are hot relative to other rhyolites. Those rhyolites typically erupt anywhere from, have emplacement temperatures of 600 to 700 degrees Celsius or lower. So this is an especially hot magma. And because it's so hot, it undergoes a phenomenon called rheomorphism, in which it welds on itself, becomes vitric and welds on itself, and can have large posts and plates to flow with large wavelength foliations as well as small wavelength foliations. You can see in the images from Henry et al. In 2017 on the bottom, you have these long wavelength folds, as well as in the pen on the right-hand side, you can see the small wavelength folds. And Hargrove and Sheridan modeled this in the cartoon in the upper part of this, to show that the rheomorphic ignimbrite is up to 1,000 kilometers thick, it's super hot, and it occurs underneath the lithium-bearing sediments. And because we know glass isn't stable in the weathering environment, especially at high temperatures, this thick accumulation of vitric ignimbrite would have devitrified. As the caldera lake was filling in over hundreds of thousands to 1 million years, and this devitrification and degassing process would release a lot of lithium and other trace metals and ligands into the groundwater system immediately above the tuff throughout the caldera. And I will have a side note here saying that studies looking specifically at the post-eruptive lithium transport are few and far between, in part because it's pretty difficult to measure. Although some studies, especially recently, have started to look at it. But some papers have shown that lithium concentration in obsidian, like this guy right here, versus its devitrified equivalent, have considerable drop-off in lithium content, showing that the lithium that was once in that intercaldera tuff that looked like this is now escaped through fumaroles into the gas chamber. Into the overlying sediments. Now, a fun way to visualize this is through the Valley of 10,000 Smokes. The Valley of 10,000 Smokes is aptly named because it's a valley near Katmai volcano in Alaska, into which outflow ignimbrite from the Nova eruption flowed. And it's on average meters thick. It started closer to the event around 130 meters and went away to essentially nothing far from the vent. But this erupted in 1912, and the first people to really get a good look at it went there in 1917. You can see this picture in the upper right corner, and they called it the Valley of 10,000 Smokes, and I think you can see why. In the centennial study of this eruption by Wes Hildreth and Judy Fierstein, they noted that by 1940, only about 10 fumaroles were still active. And compare that to the photo at the bottom right, where you see in 1982, it's completely gone. It's completely done degassing. And researchers have documented within the fumarole pipes, which you can see on the bottom. We had a great dog field assistant that helped in 1934, but you can see the human for scale in 1989 in these fumarole pipes, where they've shown that there's high temperature vapor transport of minerals like molybdenum, zinc, copper, and other ligands. And recently, a paper that just came out showed that lithium concentration in fumarolic supplements actually increases when you have higher concentrations of chlorine. And so you can see that work is starting to really try to understand how lithium is mobilized during this process. So that's all well and good, but how long did it take? Because if it happened in the Valley of 10,000 Smokes within a couple decades, that's really probably can explain the great thickness we see at the McDermitt Caldera Lake. Work by Castor and Henry and others have shown that the lake was actually active probably up to 1 million years after the eruption, and that diagenesis was probably happening maybe 50,000 to even 1 million years after that. So to look at this, there's not really, no studies have been done on this to show this specifically, but we can use one of the best studied eruptions in the world, the Bishop Tuff in Eastern California, which erupted and formed the 760,000 year old Long Valley caldera. Wallace and others at the University of Oregon used melt inclusions and complex heat equations to determine the rate of post-eruptive cooling of a 50-meter outflow sheet of the Bishop Tuff. And those data points are shown, those blue dots there. And the axis here and the y-axis is the cooling rate. So how fast does this tuff cool? The x-axis is the emplacement temperature. And so you can see that at 450 degrees C, it's a very fast cooling rate. I realize I'm running out of time, so I'll talk faster, I'm sorry. At 600 degrees C, it's a much cooler, slower cooling rate, drops precipitously. And so if we fit an equation to that, and then we model the tuff of Long Ridge at 50-meter outflow sheet. This is not the intracaldera tuff, just the outflow sheet. You can see that it corresponds to about 0.04 degrees year cooling. And now if we play around with the numbers, we can see that if you look at the bold there, it would take a 50-meter outflow sheet of the tuff of Long Ridge about 20,000 years to cool below the boiling point of water, dropping from 800 to 100 degrees C. However, because the that's the outflow sheet. If we look at the intracaldera tuff, which is up to 1,000 meters thick, the cooling rate would likely be drastically lower, meaning that tens of thousands to hundreds of thousands of years for this degassing and devitrification to take place. And so this quick and dirty calculation shows that it would take at least 20,000 years and up to hundreds of thousands of years to degas this tuff. And as a result, the large mass of lithium and other fumarolic elements like molybdenum, arsenic, and sulfur that Castor and Henry, Ingraffia et al. observe will be introduced into the basal part of the caldera lake sequences for a very long proportion of time. And this is consistent with the observation that lithium occurs throughout the whole caldera and not just within localized hydrothermal systems. So now, how does this relate to mass? We know we have a mass issue with just the first two problems. But if we calculate using this very conservative estimate, 500 cubic kilometers of intercaldera tuff, approximately 70 ppm glass, and a tuff comprised of 90% ash, and only 1% of the lithium that actually escapes, becomes incorporated in the clays, this comes to 480 million tons of LCE, which, if we look at a summation of all the masses, 90 plus 120 plus 480 equals 690. We made it. We hit 640. That was estimated by Castor and Henry. So, in conclusion, we saw that there are three main separate components involved in the formation of the Thacker Pass lithium deposit. One, in blue, is the leaching of lithium from the outflow ignimbrite by meteoric water and deposition of the liquid into the basin, which is what we see in brine deposits as well. That contributes approximately, and these are rough calculations, 90 million tons of LCE. Secondly, what we see in other lithium deposits, sedimentary deposits in Nevada, diagenesis of tuffaceous sediments within the basin, where it's being altered to clay under its own heat and weight, and that accounts for approximately 120 million tons of lithium. However, what distinguishes Thacker Pass from all of these other deposits, which is this caldera-wide fumarolic degassing for up to hundreds of thousands of years of the intracaldera ignimbrite, and the combination of all three of these components is consistent with the calculations done by Castor and Henry, showing that there's roughly 640 million tons of lithium in the caldera lake sequence. And if you take away that third component, other sedimentary lithium deposits, while they're there, they have lithium, they just don't have the grade or the size that we have at Thacker Pass. So, like I said, I'll return to our punchline. Thacker Pass is of exceptionally high grade and size relative to other sedimentary deposits because it formed within a caldera atop the gassing intercaldera ignimbrite, a unique feature not observed in any other sedimentary lithium deposit. With that, I will take any questions. Thank you for your time.
Okay, thank you very much, Tom. That was a fantastic talk. And boy, there's I'm sure a lot of questions for Tom. There are different ways that you can ask a question. You can ask via chat, and I can repeat the question to everybody. You can also use the microphone feature. I think it's at the bottom of your screen. Since I'm a co-host, I don't actually see that. But you can unmute yourself and ask a question directly. So with that, are there any questions? James?
Oh, hey, how you doing, Tom? That's awesome, excellent talk. Really well done, spectacular. I had a question for you, and I guess this kind of expands to all the others in the lithium space. What are some implications on the metallogeny of lithium? So we know there's definitely like there's usually a oceanic to continental subduction component with a rhyolitic melt that goes up. Then we have several eruptions and then a concentration of it through that. But thinking about where the next McDermitt will be, or the next Salar de Hombre Muerto, or the next green bushes, perhaps maybe it's the Rio Tinto Jadar deposit in Serbia, which was a tectonically sealed basin with captured seawater. Where is the next one going to be? And from that sort of perspective, I was wondering, with all this information gathered here, looking at how you have the ignimbrite that released all the lithium upwards and it was caught into the lake, and the other factors which contributed lithium to the system, where might be the next one? Like, what sort of system will we be looking next, and other places that we might even find a fossilized version of the brines and things we see today, which are easily exploited, but there's definitely more of these in the rock record, and how could we go find them?
I think the short answer there is, if I told you where I thought it would be, I wouldn't be doing Lithium Americas any any service there. But the long answer is this was the one whole, as you know, one whole chapter of my PhD work that was published in Nature, and the main driver we see there is that if you want a magma that's enriched in lithium, you have to chew on continental crust. As much as I would love to do exploration work in Hawaii, I can't do it. I can't justify to Lithium Americas that I need to go do exploration work in Hawaii because it's very thin oceanic crust. However, because we go back to that principle of lithium is an incompatible element and wants to jump into the melt, when you're in thick continental crust and you're melting that crust, the lithium that's in that crust will preferentially jump into that type of melt. So if you have an S-type granite, for example, where you just start melting crust, you're going to have lithium enrichment in that initial magma. And so when my advice for people who are exploring would be to look on continents, don't look in Hawaii as much as you want to go there, but also Sinti Lee and others just had a paper come out, also in Nature Communications, about lithium systematics and global arc magmas. And it was a really great paper. I was fortunate enough to review it. But one of the things that I think they missed was that they said, oh, the lithium brine deposits are associated with arcs. And you see that. But when in reality, if you look at while some of the slars may be right on the arc, the volcanic sources are actually in the back arc. They're not on the arc itself. They don't have quite the arc signature. So it's actually, the lithium is coming from the continent, even though it's in an arc setting, it's likely coming from the melt. It's not coming from those beautiful stratocones that you see all along in the Andes there. It's coming from the caldera forming rhyolitic ignimbrites to the east. So that's my advice for exploring for lithium.
Okay, Tom, we have a lot of questions popping up on chat. I'm going to read one. It's from Real, I'm not sure which. What are the differences in terms of sedimentary geology and lithium grade between Thacker Pass and Southwest Exploration Basin, North Exploration Basin, and Western lithium lenses 2 and 5 in the same McDermitt Caldera? Not sure if you know what reference that's to.
Right. Well, I think I can sort of piece that together. I think the question is, elsewhere in the caldera, Lithium Americas is doing exploration, and how does the grade and ore vary in different parts of the caldera? And the short answer is it's remarkably consistent. It is, like I mentioned in the talk, if you look at in that MATLAB 3D rotating drill hole, you can see the beautiful band of high-grade lithium throughout the whole caldera. And that includes that animation included part of the Southwest Basin. While we haven't drilled everywhere, we have the mining claims to most, if not all, the caldera, and we are actively exploring to try to understand how exactly it does vary. One thing we want to do is for environmental regions, sage grouse habitat up in the Montana mountains, north of the pit, we want to avoid that area because there's more than enough lithium in this caldera. You saw the numbers from Steve and Chris that show the vast amount of lithium that's in the caldera. We don't need to go into environmentally sensitive areas. We can stay down in Thacker Pass and mine that. The current mine life is 40 years at 20 to 40,000 tons of lithium per year. So it's a huge deposit, and if it needs to be expanded, we can easily do that because it is remarkably consistent.
Could I jump in with a quick question?
Yes.
Sure, go ahead, William.
Real quick, and I wrote it down. I just thought I wrote it down instead of it doing on chat. And the question is related to what you just talked about. How does the concentrated percentage of lithium that's so high in Thacker Pass then therefore help with the ultimate cost of mining the lithium?
Well, that's starting to get a little bit out of my pay grade, the cost of mining, but I do know a little bit about it. Obviously, the higher grade of it, if we want to mine this rock right here, it's going to have, say, 70 ppm lithium. To get the lithium out of it is going to be a lot more, a massive lithium out that you want to sell to Panasonic or whomever is going to cost a lot. The higher grade resource, the better it is from an economics perspective. That's just first principles. However, there's a bunch of factors that go into designing the pit. We're in the middle of our definitive feasibility study now, where we're playing around with the numbers and the knobs in the pilot plant to really understand what makes it most economic. And we have the best minds in the lithium industry on this. Rene LeBlanc, he is the CTO, and along with Brett Raby, they are leading the metallurgical side of things, where they're trying to really optimize this process using sulfuric acid to leach it. And that includes the block model that's being developed by Randall Burke, our head geologist at Thacker Pass, as well as North American Coal, our mining partner. And so all of these, our team is all working together to really try to do exactly what you say. We're at Thacker Pass itself. What block of our block model will give us the most value based on the process, the price of lithium, and the cost of mining?
Steve Sullivan, you have a question.
Yeah, Tom, listen to your stuff on Global Lithium podcast and things like that. Fantastic. My question is, with Thacker Pass, what's the most troubling contaminant or the hardest to get out of the material for battery grade lithium?
I don't know that I can speak exactly to those elements per se, but I know in general, it sounds like you're a lithium aficionado. You know that potassium contaminants, magnesium, calcium, all these elements present a problem. For battery grade lithium, what that means, in simple terms, is in this cell phone here, the battery manufacturer wants, say, I'm going to make this number up, so don't quote me on it, under 10 parts per billion potassium in that battery. So in order for us to sell the lithium to Apple, to Tim Cook, we to meet that standard. And so that's why it's such a complex, people don't like calling lithium a commodity. It's a complex lithium chemical industry because each battery manufacturer has different standards. So you actually are best to design your process to fit that specific customer. So whether we produce lithium that will eventually end up in my iPhone or end up in a Tesla that I hopefully one day will be able to afford, we will have to adjust the process and change the dials according to that metric. It probably doesn't really answer your question, but that's my 2 cents.
Okay, a bunch more questions. So Jillian, you have a question?
Hey, Tom. Well, I mostly just wanted to say hello, but I also was wondering what your deepest drilling, how deep you drill when you drill for these, either for the brine or for the actual lithium deposit. How deep are you drilling?
So it really depends on the deposit. At Thacker Pass, I think our deepest drill hole is about.
Oh, no.
Oh, no. Did he freeze?
He's been frozen in time.
At Thacker Pass, it's about 300 feet down.
300 feet. Okay, thank you.
Oh, am I still
Tom,
frozen?
you froze. You're better now.
Oh, it says I'm unstable. How did
What's your deepest hole, Tom?
Oh, yeah, I'm not exactly sure. I have to look it up. My problem is I came from academia where everything's in meters. And then I come into the mining world and everything's in feet. And it like throws me through a loop. So numbers are hard sometimes.
Numbers are hard sometimes.
Order of 200 to 300 meters, maybe 600 feet.
Got it.
Brine deposits much deeper. We go down to like 1,000.
Oh.
And that's like similar to oil, which is what Jillian is my former lab mate from Stanford, everyone.
Ah, cool.
Hi.
So Tom, I've got just a general question about caldera geology, and that is, rhyolitic calderas are pretty common in some geologic settings, including the Great Basin. And many calderas have pretty thick intracaldera tuff prisms. They also have early caldera lakes associated with them. I think the Bishop Tuff is a great example with, fairly thick sediments within the intracaldera setting. So you made it sound like lithium deposits are Thacker Pass is fairly unique, but this phenomenon of caldera lakes and thick intracaldera tuffs is common. So why aren't there more lithium deposits, or are we just not exploring enough?
Well, I'll say this, my response will lead with what I thought. I would come in and go to every caldera and find a million lithium deposits. I've been to probably about nearly 50 calderas in the US doing exploration work, and the only one that I found lithium in so far is Thacker Pass. And a lot of this has to do with, in the Nevada, you had this great Oligocene ignimbrite flare-up, right? And these are calc-alkaline magmas. They don't have high lithium contents to begin with. That's one factor. And whereas in McDermitt, you have this Yellowstone hotspot that's literally melting the crust itself. Obviously, there's some mantle input there, leading its alkaline nature, but you are melting thick continental crust. It's not slab rollback related volcanism. That's one. The second factor that's really important is having a closed basin. Lithium wants to get away. It doesn't want to be there. So that's why salars are such great deposits, because it's the lowest of the low in terms of elevation, not in terms of how great of deposits they are. But it catches it all. If you go to McDermitt, we know it was a closed basin. We have that diagenetic profile. It's still closed to this day. If you look at its beautiful close, there's some erosion that happened recently, but the Thacker Creek that goes through there. But it's been a closed basin for a long time. In the case of Long Valley, that's a great question. The Caldera Lake, if you look at the papers by Wes Hildreth and others, it was not closed. The Owens Gorge cuts right through the margin, and the lake drains. You have a few tufaceous sediments and sequences, but it's not been a closed lake, and that's a young system.
Okay,
relatively young.
that's a good.
So I think that the having a closed basin in which these sediments are forming, and then you have the degassing of the tuff, is a really essential component of the puzzle, in addition to that first component, which was having the high magmatic concentration of lithium.
I think the peralkaline nature is critical also.
Yeah, and Tom made a point of that. Okay, on a related note, Chris Henry has a question, and that is, Tom, you worked on the caldera north of McDermitt, and there's the whole Yellowstone track of calderas. Do any of these have significant lithium in them? And that would sort of go along the lines of what Sandra just talked about in peralkaline magmatism. You've got other calderas in the hotspot track. What about Yellowstone? What about some of these others?
There are a couple factors. That's a great question. That was my first targets was to go along those track along the Yellowstone hotspot. The Snake River Plain is, say, I'll lowball it. Probably 90% of the calderas that erupted associated with Yellowstone occur in the Snake River Plain are covered by nearly a kilometer of basalt. So there's no way you're going to access that. Maybe some of the deep drill cores that have been done throughout there could assess that. But I don't think it would be ever economic to mine that much basalt. That's one. The second point is, in the case of McDermitt calderas, we know that some of those were not closed basins. There were freshwater lakes. We know that by the presence of diatoms. There's the really diatomaceous caldera lake sediments in the north part of the caldera, in the North Whitehorse calderas. So we know that you don't have this alkaline, saline water that is required that we see down at McDermitt. So they're also not incised there. There's not much erosion there that has been done in northern McDermott. Yeah, and at Yellowstone, you're not going to mine Yellowstone National Park. So I haven't looked there. So yeah, those are my
There's
thoughts
actually
on
some pretty good literature on Yellowstone National Park, lithium in sediments by the USGS.
that.
Are there peralkaline eruptions at Yellowstone or no?
No, they're not really peralkaline. The Huckleberry Ridge, I don't know if you'd call it peralkaline, or it's certainly, high potassium magnetism. Okay, another question.
Another thing interesting to note on that point is, I said in the beginning of the talk, lithium doesn't want to be partitioned into any sort of crystalline phase in a magma chamber. So that means its partition coefficient is less than 1. The only mineral, and there's only one tuff, to my knowledge, in all of the Snake River Plain that has any sort of hydrous phase, which is, I think, the Arbon Valley tuff. It's Arbon something. It's about 6 or 8 million years old, somewhere around there, and it has some biotite in it. So that would be the only magma. This is just arm waving here. I don't have any evidence to back this up, just off first principles, in which there could be lithium partitioning into a magmatic crystal, which could be biotite, because biotite has a partition coefficient of about 1, and then you start so that's one thought I have.
Somebody named G has a question. Are there any other locations in the world that has the scale and quantity and quality of lithium of Thacker Pass?
Not that I have found, not that exist that I know of, that anyone's reported. I will say the highest, you have spodumene, for example. Those crystals itself of spodumene in the hard rock deposits have 2%, 2 to 4% lithium oxide by weight. We did in situ analysis of the clay, so not the whole rock at Thacker Pass. It has pretty much exactly the same composition. So I would venture to say that the lithium at Thacker Pass is the highest grade minerals of a resource out there. Of course, there's some minerals here and there, but in terms of a lithium deposit, I don't think it gets any better than that. Greenbushes is known as the highest grade spodumene out there, and Lithium Nevada Thacker Pass project has the same concentration in the clay as the spodumene.
Other questions?
You know what the
Sandra.
mining plan is?
Yes, the mining plan is there. It's actually, we nearly done permitting. We had a public comment period that's over, and the final decision will be finished in January. So we should be geared up and fully permitted by mid-January, right around inauguration. And that's that. And then we're just then it's just a matter of getting the funds to construct. So it's actually happening, which is really exciting.
Any other questions?
Hey, Tom, this is a little bit out of, it's not a question regarding to lithium, but could you go back to that screen that had the world map with all the lithium reserves? I'd like to see that again. I didn't get enough time to admire that map.
Let's see, how do I do this?
You can share your screen again, Doc.
The world one, right? Yeah, there we go.
Yeah, and then while we're here, I'd just like to say this is an amazing presentation. Thank you so much.
Thank you. Oh.
We've got Stephen and Lisa both have had their hands up for a bit. So maybe Stephen, if you want to start with your question.
Yeah, just how does Thacker Pass compare to like Bacanora down in Sonora in terms of their deposit?
Okay, so that one is, oh, there we go. Isn't that? It's higher than that. Depending on the sometimes it's hard to compare apples to apples, because you're not comparing apples to apples, because everyone has different standards for how they interpolate data. As you saw in ours, we have drill spacing every meter drill spacing because you need that for a certain level of confidence in your resource assessment. There's some projects out there that have 4 drill holes and they extrapolate out for 2,000 meters in clay projects. And it's just like, you can't do that if you want to be taken seriously. That's not to say the Bacanora project is, I will say, probably one of the top ones as well. It's not quite as, it's not as large, and it's of limited geographic extent. So in terms of scalability of a resource, it's nowhere near as scalable as Thacker Pass. However, it does have, I think their average concentration is around 2,000 or so. It's higher average than the Rhyolite Ridge or the Clayton Valley projects.
Lisa Stillings, you've got a question. Lisa.
Yes, hi, Tom.
Hi, Lisa.
So thanks for the call outs, but I want to make sure to cite Claude Morissette because it was really her work. But I have 2 questions, actually. The first is, we learned with the work that Claude did that the fact that the clays were magnesium rich was really important, that it was the exchange of lithium for magnesium in the clays that allowed the clays to gain such a high concentration of lithium. So I'm wondering where the magnesium came from. I know it's a paracrystalline deposit, but was that sufficient to supply the magnesium to the basin? And then the second question was, I was wondering if you could briefly address the challenges of extracting lithium from the clay as part of the mining process. So thank you.
Right. Yeah, I mean, that's a really good question. And that is a question for an expert like you who looks at clay mineralogy. However, I think I will say in terms of source of magnesium, you have the magnesium in the concentration in the primary magma is higher than the magnesium concentration, than the lithium concentration in the prior magma. But so from a mass standpoint, you have magnesium there. Now it's a question of, after that, how does it get to the fluids, the pore water, to create these clays? And that is, I'm not that familiar with the thermodynamics of magnesium speciation and whatnot. So I think that's a great question to consider. I will say that magnesium in pretty much all lithium deposits is something people want to try to avoid. And that sort of speaks to your second question, which is how easy it is to process. What are the challenges? I believe that was your second question. And contaminants, that's one of the big problems. You have to look out for contaminants. You want a rock that ideally has 100% lithium, right? And nothing else. But you won't get that. So in lieu of that, you have to adjust your knobs and your dials to do that. And we have a whole pilot plant, or we call it research facility now, and that's run and fully operated by full-time Lithium Americas employees in Reno, Nevada, that is looking at this question. They're working day in and day out to optimize that process to get rid of the contaminants and to reduce sulfuric acid consumption as well as water consumption and how much we burn, how much CO2 we burn.
Just along those lines, Tom, of the first question, Lisa's question about magnesium. Are you partitioning lithium or magnesium, into the gas phase on devitrification of the tuff in a similar manner that you are with lithium?
I would think it would behave roughly similar. Now, there might be people on here who are definitely people on here. I've seen some of the names that are well more qualified to talk about magnesium fluids than I am, but you would think it behaves a little bit similar. But I mean, if anyone has any.
Actually, at the end of the thesis presentation, John Bryce emailed and he suggested that a major contributor of magnesium to the system in McDermitt came from the basalts that cap the area that locally are above the sediments, and through simple erosion of the unstable minerals on the Earth's surface, that the magnesium would go and work downward into the system. perhaps this is one of the ways it was introduced.
Yeah, I don't know that I agree with that because one, the basalts are significantly younger in age than the sediments, and the timing of mineralization as determined by Castor and Henry. There's some minor basalts, but it is significantly less than 1% of the volume. So I think there's a mass problem there.
Well, you could
Probably
get in-
contribute to it, but I would say, I guess just from a general mass perspective, if you have, 1,000 cubic kilometers of rhyolite in this system here, you're going to have less than 10 probably of basalt. I don't know, Steve may, Chris may have other thoughts on that.
There's the olive rhyolite system too.
Yeah, Ken Scott has a question. Ken, are you there?
Sure I am. Hi. Can you hear me?
Yep, go ahead.
Okay. I'm a complete neophyte, so excuse me for my
Well,
question.
at least you're not a neoform, which I learned about today.
Okay. I'm trying to understand the lithium space, and I'm trying to figure out the difference between North Carolina sputamine, if I'm pronouncing that correctly, the quality comparison versus sedimentary lithium from like Thacker. And like I know just from a macro perspective, why is it that let's say Tesla signed a deal with Piedmont and announced it right away? Like why is the market kind of going towards East Coast lithium versus say Thacker Pass or that one Nevada mine that I guess it's Albermeal that owns it? What's the difference between the two commercially?
That's a good question, and it took me a while to understand the lithium space. I still don't understand it completely, but a very, very history of it is lithium used to exclusively be mined from spodumene, from these pegmatite deposits. Actually, in the Black Hills of South Dakota is where it was first mined in the U.S. Then the North Carolina deposits were mined, and then they found the green bushes in Australia and were mining that. And then brines came along, and brines, it's significantly cheaper on a per ton basis to extract lithium from brine than it is to extract it from spodumene, which is the mineral in pegmatite. Clays will be somewhere in the middle on an operating cost basis. So the reason for Piedmont being in getting a lot of attention right now is because they just signed a deal with Tesla. So they're getting some press right now, but they are one of these more expensive spodumene processes, these old processes that I like to think of it as ways the cost to take it out is pretty much proportional to the energy in which it took to form. Brines, you just have water flowing into a basin. Very low, you don't need much energy there to form the brine, and you have some evaporation. Sediments, you have to have this compaction, this diagenesis, so it's at depths and higher temperatures, less than boiling, but still at higher temperatures. Spodumene is forming in pegmatites in very deep in the earth crust at very high temperatures. And so to extract the lithium, so that means that
Shoot.
Is that a sign? I'm not sure.
Maybe.
No, he was getting somewhere.
lithium is stable in crystal spodumene. Am I frozen?
All right, now you're
You were
back.
frozen, yes.
Oh, well, I don't know
I
where
think
you
there's a time quota involved.
Oh, yeah, but I guess I would say that the energy at which it took to form is proportional to the energy at which it costs to take it out. So that's why the spodumene resources like the one Piedmont's, their operating costs are very high relative to a brine project. Clay is somewhere in the middle.
If I could
just to follow up.
If I could jump in with spodumene, it's lithium hydroxide, and it's used more in the high capacity, high nickel concentrated batteries. So if you're going to do the high nickel such as like in the Tesla or the Cybertruck, things like that, it has to be the high nickel content. For lithium iron batteries and things like that, or cell phones, it's carbonate. So it's probably going to be 50-50 in the near future, or a mix, but that's the reason why one is sort of better for the other, depending on what kind of battery you want to go with.
Thank you so much, because you actually bring me to my next question, which is I'm hearing from like, and this is just from Global Lithium podcasts and whatnot, that
Right.
there's like this effort to sort of extract from clay-based lithium a higher quality, and that's going to take like a new calculus, a new chemistry to figure out. Is that correct, or is that my understanding? Is that correct?
Yeah, I don't want to. I'll qualify this with I'm a geologist, volcanologist by trade, and I only get this information through osmosis and listening to podcasts and reading articles. I mentioned this earlier. Each battery, and Stephen said this very well, each battery requires a different chemistry, a different product, different specifications. And so you really have to, as a producer of lithium, you have to listen to your customer and what your customer wants and adjust accordingly. Now, there are some fundamental things like you were saying, hydroxide can be produced from pegmatites. What's great about Thacker Pass is that it's versatile. It can produce lithium hydroxide and lithium carbonate. And we're contemplating in our DFS what that ideal mix would be. And so there's a lot of decisions that go into that, and things that inform that decision is what I meant to say, including geology. That's one small part of it. And the other things is that the bulk of it is the engineering, and then there's the other part on the other end, which is the financial considerations. Not to say that that's less important, but you see, the bulk of that is the decision go into the engineering there.
No, but I think for like the average guy like me that's trying to understand this space, it's kind of cool. And thank you. From what I'm understanding from tonight, there really is a bifurcated market, and there's going to be such a great demand for lithium that higher quality is going to go to higher needs, like battery, cars and electric vehicles. But yet there's still going to be, batteries for phones and other kind of, commercial items that are going to be increasing their demand as well. And so, America can support both. It's just a function of, where you're looking at.
I have a quick comment for everybody. We've recorded this talk of Tom's, and all of the questions and discussion afterwards. So you guys can join us on YouTube. The YouTube link is listed on the chat. So if you go to the chat room, you'll see at the very bottom there from Molly Hunsaker, a link to the talk and questions and discussions. So I think with that, are there other questions and comments that people would like to provide, Tom?
I've got a lithium prospect. I'd like to get Tom's email address if I could.
Great. It's tom.benson@lithiumamericas.com.
Okay, thank you.
Okay.
Answer any questions people have, and also, any questions, feel free to shoot me an email, or get in contact with Mike, and he can put you in contact with me.
Thank you.
Thanks a lot, Tom. Great job, Tom. Really, really wonderful. Was very educational. You did fantastic. I
Very
enjoyed it immensely. Really good.
I agree with all those comments. Thanks, Tom.
All right. Thanks, everyone.
And thanks everyone for showing up, and join us next time. We have these talks every month.
That was awesome. Well done.
Bye.